let's create a butane molecule. It has 4 carbon atoms and 10 hydrogens. You can see here 10 hydrogens, right? So let's connect the hydrogens together. I'm Professor Dr. Mchem from Dr.Mchem Institute of Chemistry, University of St. Jamshire, and I'm very much here showing you how to prepare a butane molecule, because now we are going to study something about butane. So this is the structure, or you can say the molecular model for butane, in which you can see there it is: CH3, CH2, CH2, CH3. How many carbons? 1, 2, 3, 4. 4 carbons and 10 hydrogens. C4H10. Just look at here. You can see, well, we refer to N-butane. It is also called N-butane. N-butane means, of course, a straight chain butane, but it doesn't look like straight. You can see it has a zigzag structure, right? A zigzag structure. It doesn't look like a straight chain compound. So maybe they're, because they have the angles between them, between the of course the carbon atoms, they are very close to the and of course to the, they are similar to the tetrahedral structure or tetrahedral angles, which are almost about 109.5 degrees. So now rotations about any carbon to carbon bond is very easy and possible. You can see rotations at any carbon to carbon bond is extremely easy. Yes, that's it. So this is it, a butane molecule. I'm going to study today, make you study today, the butane molecule. Now I will show you the Newman projections also when you look from carbon number 2 to carbon number 3. That is from here, carbon number 2 to carbon number 3, right? This is carbon 2 and this is carbon number 3. So when you will look at from carbon number 2 to carbon number 3, what you are going to observe, I'm going to explain it to you, right? Now there's a question regarding staggered and eclipsed conformation, that why is it so that an eclipsed conformation. I will draw the hydrogens that are eclipsing, that are back hydrogens with the red color. Right, so these are the eclipsing hydrogens. Right, so this is the eclipsed form. Now why is it so that it's it is less stable, and why is it so that staggered conformation is more stable? So I can draw a staggered conformation also. So this is the staggered conformation, right? Now, as I just mentioned, that why is it so that staggered is more stable than the eclipsed? So this is all due to the one and very good reason, because here you can see the hydrogen atoms, they are all far apart from each other, right? Whereas if you compare it with the second one, that is the eclipsed conformation, here simply you see the reason is, of course, the eclipsing, right? Then this interaction between these two hydrogens, the eclipsing hydrogen atoms, and of course because of that there's a lot of torsional strain. Which strain? Torsional strain. Torsional strain. And what would that result into? That this conformation would be greater in energy. This would be greater in energy. You have seen that in my previous lecture, the potential energy graph, and it's when the molecule it rotates to the this eclipsed conformation, the energy increases. So this is the reason, that because of the torsional strain, right? It has a lot of torsional strain over here. It is facing the torsional strain, and resulting this conformation would be of greater in energy and would be less stable. It would be less stable as compared to the staggered one. So this is one of the reasons that why staggered is more stable as compared to eclipsed conformation. Now there are conformations which have been assigned specific names. Number one, when methyl groups are in the same direction, right? So this is a butane molecule. You can see 4 of the carbons with all these hydrogens, and these the upper ones, these are the methyl groups, right? They are facing each other, and the rest are CH2 carbon with 2 hydrogens, carbon with 2 hydrogens. Now if you simply turn it like that, right, this way, you are going to observe that the 2 methyl groups, that is the upper one, this one, and this one, they are facing each other. They are facing each other. That means the dihedral angle between them becomes 0. That means they are eclipsing. They are eclipsing each other. And this type of conformation in which the 2 methyl groups, they are facing each other, and the dihedral angle between them is equals to 0, it is called totally eclipsed. Now how we will draw this on the paper, I will show you in a minute. So I will draw it. Methyl group at this position, and of course methyl group at this position, and then hydrogen and the second hydrogen, this hydrogen in the solid wedge. So here you simply see that this type of this type of conformation is called totally eclipsed when the methyl groups are facing each other, and when as I've just showed you in this with the molecular model also, that they are facing each other. You can see here, right? They are facing each other. This is carbon number 1 and 2 and 3. This is carbon number 3. So if you look from carbon number 2 to 3, you can see them, the 2 methyl groups eclipsing each other, having a dihedral angle equals to 0, right? And this is how it looks from here. If the viewer is viewing from this end, if the viewer is from this end, right? Like if it would be like this. If the viewer is viewing from this end, how he is going to observe it? He will simply observe it like this. whereas you can see them here. When the two methyl groups, when they are facing each other, they are close to each other, they are eclipsing, and dihedral angle between them equals to 0. So theta equals to 0. So this is called the totally eclipsed conformation. This type of conformation, we call it totally eclipsed. Totally eclipsed conformation. We can also draw the Newman projection. I have shown you the molecular model, but we can also draw the Newman projection for this totally eclipsed conformation like this. The hydrogens at the back, right? So now this angle between them is theta equals to 0. This is the conformation, totally eclipsed conformation, and you can see it, the Newman projection, how the two methyl groups, they are eclipsing. And I have shown you the same thing via molecular model also, in which the dihedral angle theta equals to 0. So they are facing the torsional strain, and they will be very much high in energy. The next conformation is when the two methyl groups, that is this one, this is carbon number 2 and 3, this is carbon number 3, right? This is the first methyl group and the other methyl group. Now when the angle between these two methyl group is 60 degrees, when it is 60 degrees, right, the conformation is staggered. This conformation is called staggered. As you can see, they are far, the methyl groups are far apart from each other, right? So this is the staggered conformation, right? And the 60-degree conformation is also called gauche conformation. It's a French word, right? And it's called in gauche conformation, in which the dihedral angle, that is between the angle between these two methyl groups is 60 degrees. You can see here the angle between them is 60 degrees, and they are far apart from. So I was telling you about the gauche conformation, in which the angle between the two methyl groups, that is this one and this one, is 60 degrees, right? This is carbon 2, carbon 3, and this is the staggered conformation. You can see the staggered conformation easily, as the methyl groups are far apart from each other, right? And this is how it looks like. The butane molecule is in the staggered form, and methyl groups are, you can simply see that you can see the right or left, or they are far apart from each other. It's also called, it's pronounced as gauche conformation. I will draw the structure. This is the model. Then I will show you the Newman projection, how it looks like. You will judge also this molecule from that angle. So this is how, when the molecule, when the viewer is viewing from this end, right? He's viewing from this end. How does it looks like? CC CH3 CH3 H and H and H. So this would be this is supposed to be the structure when the angle between the two methyl groups, when the viewer will view from this side, this side, he's going to view that the angle between the two methyl groups is 60 degrees. these two will have a 60-degree angle, right? 60 degrees angle. Okay, so what would be the Newman projection, how it would be like? I'll show you right now. So the angle between these two methyl groups would be 60 degrees. This is it, 60-degree angle over here between these two methyl groups, and this is also called Gauch, gauge, that is 60-degree angle. We can pronounce it as gauche, right? So this is the staggered conformation, and when the angle between the two methyl groups is 60 degrees, you can see they are far apart, the methyl groups are far apart from each other. So these are the three drawings I've shown you. The Newman projection, and of course this 2D drawing on the board, and then of course I've shown you the model also, this one, right, in which the methyl groups are simply eclipsing. I've shown you the eclipsing of the two methyl groups. When they are not eclipsing, they are having a 60-degree angle. They are not eclipsing, they are having a 60-degree angle. I've shown you that also. So that was it. Now let's jump to the next conformation. Now there is another conformation in which you can see here the carbon 1, carbon 2 and 3. Now you can see the angle between this methyl group and this methyl group is 120. This angle and this angle becomes 120. This is the angle between this methyl group and this methyl group. It is this angle is 120. You can see here 120 degrees. This methyl group and this methyl group. The angle between them is 120. So here you can simply see they are also eclipsed conformation. This is also an eclipsed conformation, right? Here you can see the two hydrogens, they are eclipsing. Here you can see of course a hydrogen and the methyl group, they are eclipsing, right? And this hydrogen and this methyl group, they are also eclipsing. So this is also an eclipse, but the angle between the two methyl groups is 120. So we call it the eclipse conformation again, right? I'll draw the Newman projection for this so that you'll have a clear cut idea. This is the front carbon with the hydrogens and the methyl group. This is the back one, hydrogen, and this is a methyl group at the back. Okay, and this is the second hydrogen. Okay, so now which angle we were talking about? We were talking about the angle between these two methyl groups, which I just showed you. It was 120 degrees. This was 120 degrees, and this is also called an eclipsed 120 degrees angle, right? And it's 2D structure can also be drawn. I'll show you now. methyl group, hydrogen, 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 and a methyl group. So this is again when the methyl groups are at 120-degree angle apart from each other. This is the Newman projection and of course the 2D formula of our conformation, the eclipsed conformation for butane. I hope you got the idea from the three structures, because I've shown you the the model, then the Newman projection. I've shown you this model first, this one, right? I've shown you the angles between the two methyl groups. They were 120 degrees, and then I've shown you the Newman projection and then the 2D formula. Another staggered conformation in which the methyl groups are just at the opposite sides, that is, they are anti, they are opposing each other, they are on the opposite sides. You can see one and this one, right? They are opposite sides, on the opposite sides, right? And this is called anti because methyl groups are opposing each other. The two methyl groups are opposing each other. Now this is again staggered conformation, so it will be again lower in energy than of course the eclipsed conformations, right? Because these conformations are lowest in energies because these methyl groups, they are very bulkier and they are far apart from each other. They are as much far apart as possible, and they are just on the opposite side, you can see. So they are far apart from each other. So that's why all of these conformations, four conformations, the anti and gauche, are the lowest in energy. And then of course the eclipse conformations, and the anti conformation is the lowest. It's the lowest in energy, and as I've just mentioned, because if the bulkier methyl groups are as far apart as possible. Whereas the gauche conformations, it has got the methyl groups and they are apart from each other with a 60-degree angle, right? And it is almost about 3.8 kilojoule, that is 0.9 kilocalories higher in energy than the anti conformations. And it is because of the fact that the methyl groups are what happens that the methyl groups, they are very much closer, so their electronic clouds, they begin to repel each other, and this is because of the fact that we can simply see that the methyl groups, they'll crowd around. There's a crowding of methyl groups there. So this was something about this conformations. Now I will show you the potential energy graph also, how it goes on against the dihedral angles, potential energy versus dihedral angles starting from 0, 60, 120, 180, 240, 300 and 360 degrees. With the totally eclipsed, then gauche, then eclipse, then again anti. As the molecule rotates, these are all the names of all those rotations of that conformation, conformers, right? And then eclipse, then gauche, then again totally eclipsed. So I hope you have understood by with the help of this molecular model how you can see the torsional strain also, and how you can see the different conformations, how they are eclipsing, and what angles are forming, and what conformations are called, why they are named differently. So this was something about conformations of butane. Now this is a potential energy diagram versus dihedral angle. Now here you can simply see as the molecule rotates. Now here the anti-conformation, which is around at about 180 degrees. This is it. It's the lowest in energy, right? Whereas the totally eclipsed, that is here around this one is highest in potential energy. You can see this is highest in energy, and this one, the anti-conformation, it is the lowest in energy. So almost around here you can see this much, that is, this one is around 15 kilojoules, whereas here the potential energy, when it rises to the topmost, it's almost about 5 kilocalories or minus 21 kilojoule. So this was the graph between potential energy versus dihedral angle of this butane molecule, in which you can see the totally eclipsed and the anti-conformations. The totally eclipsed conformation is highest in energy. You can see here it is highest in energy, whereas the lowest in energy is the anti-conformation, which is this one, in which the methyl groups are as far apart as possible, where they are facing the torsional strain, right? As the methyl groups are close enough, they are even they are having a strong repulsion between their electronic clouds, because the methyl groups are extremely close together. So this kind of interference between the two bulkier groups is also called steric strain, or this is also called a steric strain or steric hindrance that is formed between the two methyl groups, right? When they are close enough, when they are extremely close together, when they are in the eclipsed conformation, right? So this is also called a steric strain or a steric hindrance. So as I just told you, because of the end methyl groups are extremely close enough, whereas here they are as far apart as possible, right? So they are at the anti position, and that's why they are called opposite sides. So they are called anti, and they are lowest in energy. You can see here they are lowest in energy, right, at 180 degrees. So this was something about the potential energy diagram. So I hope you like this video. Please go through it and learn it from the molecular models and everything. And see you again with something interesting and something new and more exciting. Thank you very much. Bye bye.